In this video, we are going to be talking about how to multiply and divide radicals. We're going to begin by talking about multiplying radicals. So the product property for radical states that if you have the square root of a times b, that will equal the square root of a times the square root of b. And the opposite is true. The square root of a times the square root of b will equal the square root of a times b. So let's use this property right here to be able to multiply the square root of 2 times the square root of 2. The square root of 2 times the square root of 2 will be the square root of 2 times 2, which is the square root of 4. What is the square root of 4? 2. So here our answer is 2. On example B, the square root of 4 times the square root of 2, well, 4 times 2 will give me the square root of 8. And then from here, we can simplify the square root of 8. I'll use the birthday cake method. The smallest prime number that goes into 8 is 2, goes in 4 times. The smallest prime number that goes into 4 is 2, it goes in 2 times, and 2 goes into itself once. When you get to 1, you're done. That's the candle to your cake. Here I'm looking for pairs of numbers to leave the square root symbol. So 2 will leave the square root symbol. This 2 does not have a pair, so this 2 will stay home. So here my final answer is 2 square roots of 2. So it says, according to the product property for radicals, we can multiply unlike radicals. So on example 2, we have the square root of 3 times the square root of 12. Well, that's going to equal the square root of, what is 3 times 12? 36. Is 36 a perfect square? Yes. What is the square root of 36? 6. This is our answer. So you always want to multiply first and then simplify. Let's try that again with example 3. The square root of 5 times the square root of 8 will give us the square root of 40. Is 40 a perfect square? No, so I'll have to do the birthday cake to simplify that. The smallest prime number that goes into 40 is 2, it goes in 20 times. The smallest prime number that goes into 20 is 2, it goes in 10 times. 2 goes into 10 5 times, and 5 goes into itself once. So I have a pair of 2's that can leave the square root symbol. This 2 and this 5 are both staying inside. 2 times 5 is 10. So our answer here is 2 square roots of 10. Go ahead and pause this video and try example 4. The square root of 4 times the square root of 8 is the square root of 32. 32 is not a perfect square, so we'll have to do birthday cake for 32. The smallest prime number that goes into 32 is 2, goes in 16 times. 2 goes into 16 8 times. 2 goes into 8 4 times. 2 goes into 4 2 times, and 2 goes into itself once. So I'm looking for pairs of numbers to leave the square root symbol. Here I have 2 pairs of 2's that can leave. 2 times 2 is 4. This 2 does not have a pair, so that 2 is staying home. So here my answer is 4 square roots of 2. If we look at example 5, now I have a coefficient out in front. You want to multiply your coefficients together and then multiply your radicands together. Remember, radicand is another name for the number underneath the square root symbol. And then we can simplify. So let's try that now. I have 5 square roots of 24 times the square root of 2. My coefficient is 5, and then the coefficient of the square root of 2 is 1. 5 times 1 is 5. And then I'm going to multiply my radicands together. 24 times 2 is 48. Now we want to simplify this. I'm going to go ahead and write down my coefficient of 5. That way I do not forget about it. And I'm going to do the birthday cake for 48. 2 goes into 48 24 times. 2 goes into 24 12 times, 2 goes into 12 6 times, 2 goes into 6 3 times, and 3 goes into itself once. So here I have 2 pairs of 2's that can leave the square root symbol. This 3 does not have a pair, so that 3 is going to stay home. So when I simplify this, 5 times 2 is 10. 10 times 2 is 20. So my answer is going to be 20 square roots of 3. Go ahead and pause the video and try example 6. On example 6, my coefficients are -4 and 1. -4 times 1 is -4. My radicands are 3 and 27. If I multiply 3 by 27, I get 81. So right now I have -4 as my coefficient. Is 81 a perfect square? Yeah, the square root of 81 is 9. Well, I can multiply -4 times 9. That's going to give me -36. That is my answer. On these examples, we've had monomials, meaning one term being multiplied by one term. So all of these were just monomials being multiplied together. If we look at examples 7 and 8, here I have one term being multiplied by two terms. So a monomial being multiplied by a binomial. Same thing here, one term being multiplied by two terms. For these problems, we're going to use the distributive property. Same rules are going to apply, so let's try that together. The square root of 6 times 3 square roots of 5. Well, 1 times 3, if I multiply my coefficients together, is 3. And then I'm going to multiply my radicands together. 6 times 5 is 30. Minus the square root of 6 times the square root of 20. Well, 6 times 20 is 120. Now that I've multiplied, my next step is to simplify. I'm going to bring down my coefficient of 3, and I'm going to do birthday cake for 30. The smallest prime number that goes into 30 is 3. Goes in 10 times. The smallest prime number that goes into 10, ooh, that's a lie. Smallest prime number that goes into 30 is 2. Goes in 15 times. Smallest prime number that goes into 15 is 3. Goes in 5 times. And 5 goes into itself once. When you get to 1, you're done. That's the candle to the cake. Do we have any pairs here? No. So the square root of 30 is as simplified as it's going to get, so that's going to stay that way. I'm going to bring down my minus sign, and now I'm going to do birthday cake for 120. The smallest prime number that goes into 120 is 2. Goes in 60 times. The smallest prime number that goes into 60 is 2. Goes in 30 times. 2 goes into 30 15 times. 3 goes into 15 5 times. And 5 goes into itself once. Here I have a pair of 2's that can leave the square root symbol. 2, 3, and 5 do not have pairs, so they are going to stay inside. So that's going to give me 6 times 5 is 30. So now we want to look and we want to see if we have like terms. Do we have like terms here? Yeah, they are both the square root of 30. So I can add these like terms, or in this case, subtract. What is positive 3 minus 2? 1. So we're going to have 1 square root of 30, or you could just write the square root of 30 as your answer. Go ahead and pause the video and try example 8. So on example 8, we're going to use a distributive property. The square root of 3 times 5 square roots of 2 will give me 5 square roots of 6 plus the square root of 3 times the square root of 3 is going to be the square root of 9. So let's go ahead and try to simplify this. If I do birthday cake for 6, I will see that I don't have any pairs. So 5 square root of 6 is going to stay that way. What's the square root of 9? The square root of 9 is 3. It is a perfect square. Is 5 square roots of 6 and 3, are these like terms? No, these are not like terms. There's nothing else I can do for this one. This is my answer. On example 9, here I have a binomial being multiplied by a binomial. 2 terms being multiplied by 2 terms. You could use FOIL for this. You could use the distributive property for this. For all problems like this so far this school year, we have used the area model, so I'm going to continue to use the area model. So I'm going to take one of my binomials and write it down the side, and I'm going to take the other one and I'm going to write it across the top. If you have these switched, that is okay. It doesn't matter which one you put on the top and which one you put on the side, so long as you are remembering to multiply them by each other. So let's see. 1 times 1 is 1. 1 times the negative square root of 13 is the negative square root of 13. 1 times the positive square root of 13 is positive square root of 13. And the square root of 13 times the negative square root of 13 is negative square root of 169. Be careful. The negative is on the outside. It's not on the inside. Negative on the outside, not on the inside. So just be careful with that. So now let's take what we have inside of our area model, and we are going to go ahead and combine like terms and simplify. So I have 1. What's the square root of 13 minus the square root of 13? 0. So I'm not going to include that as a part of my answer because they cancel. Minus, oops, let me get my pen back here. What's the square root of 169? 13. Well, I have like terms. What's 1 minus 13? Negative 12. So my answer here is negative 12. On example 10, we have the square root of 5 plus 2 squared. Well, we know that that means that we have the square root of 5 plus 2 times the square root of 5 plus 2. 2 terms being multiplied by 2 terms. You could FOIL, you could use a distributive property twice, or you could use the area model. Doesn't matter to me what method you do. I've been consistently using the area model, so I am going to continue to do that. So let's multiply these together. The square root of 5 times the square root of 5 will be the square root of 25. The square root of 5 times 2 will be 2 square roots of 5. 2 times the square root of 5 is 2 square roots of 5. 2 times 2 is 4. So let's see what we have. What's the square root of 25? 5. And then I have 2 square roots of 5 plus 2 square roots of 5. These are like terms. When we add these like terms together, what do we get? 4 square roots of 5. Plus, I still have this 4 hanging out down here. Do I have any like terms? Yeah. What's 5 plus 4? 9. So my answer is going to be 9 plus 4 square roots of 5. These are not like terms, so there's nothing else that you can do with this one. So this is your answer. Go ahead and pause the video and see if you can try examples 11 and 12 on your own. On example 11, I'm going to go ahead and set up my area model. So I have the square root of 3 plus 3 and the square root of 3 minus 4. The square root of 3 times the square root of 3 is the square root of 9. And then I'll have negative 4 square root of 3, 3 square roots of 3, and then 3 times negative 4 is negative 12. So let's start by looking at the square root of 9. Can we simplify that? Yeah, what's the square root of 9? 3. Whoops. Then I'm looking at my like terms. What's 3 square roots of 3 minus 4 square roots of 3? It's negative 1 square roots of 3, or just the negative square root of 3. And then I have minus 12. Do we have any like terms here? Yeah, 3 and negative 12 are like terms. What's 3 minus 12? Negative 9. Negative 9 and the negative square root of 3 are not like terms, so this is my answer. On example 12, the square root of 5 plus the square root of 2 squared means that we have the square root of 5 plus the square root of 2 times the square root of 5 plus the square root of 2. So I'm going to go ahead and do the area model for that. So the square root of 5 times the square root of 5 is the square root of 25. The square root of 5 times the square root of 2 is the square root of 10. The square root of 2 times the square root of 5 is the square root of 10. And the square root of 2 times the square root of 2 is the square root of 4. Can we simplify the square root of 25? Yeah, the square root of 25 is 5. Plus, I have like terms. What's the square root of 10 plus the square root of 10? 2 square roots of 10. Can we simplify the square root of 4? What's the square root of 4? 2. Do we have like terms now? Yeah, what's 5 plus 2? 7. So my answer is 7 plus 2 square roots of 10. That is how you multiply radicals. Let's move on to dividing radicals. So the quotient property for radicals state that the square root of a divided by b equals the square root of a divided by the square root of b. And the square root of a divided by the square root of b equals the square root of a divided by the square root of b. Let's look at that on example 1. On example 1, we have the square root of 25 divided by 10. Well, the square root of 25 is a perfect square. The square root of 25 is 5. Can I reduce the fraction 5 over 10? Yeah, I can reduce both the numerator and denominator by 5 and get 1/2 as my answer. On example 2, I have the square root of 64 divided by the square root of 16. Well, 64 is a perfect square. What's the square root of 64? 8. What's the square root of 16? 4. What's 8 divided by 4? 2. So you always want to simplify as much as you can with these problems. A radical expression is not simplified if there is a radical in the denominator. We must simplify the radical in the denominator first by factoring out any perfect square factors or using birthday cake, and then multiply both the numerator and the denominator by the simplified radical. This is the process called rationalizing the denominator. and I'm going to show you how to do that. So on example 3, we have 5 divided by the square root of 7. We cannot have a radical in the denominator. So to get rid of the square root of 7 in the denominator, we're going to multiply the denominator by the square root of 7 and the numerator by the square root of 7. 5 times the square root of 7 is 5 square roots of 7. What's the square root of 7 times the square root of 7? The square root of 49. So we have 5 square roots of 7. In our denominator, what's the square root of 49? This is our answer. Our denominator has been rationalized. We no longer have a square root in the denominator. Let's try that again with example 4. We have 9 divided by the square root of 3. So here, to rationalize the denominator, I'm going to have to multiply both the numerator and the denominator by the square root of 3. So I'm going to have 9 square roots of 3 divided by the square root of 3 times the square root of 3 is the square root of 9. So I have 9 square roots of 3. And then in our denominator, what's the square root of 9? 3. In this problem, I could not simplify this 5 and the 7, our outside numbers, any further. Can I simplify my outside numbers here, this 9 and this 3? Yeah. What's 9 divided by 3? 3. So this is going to give me 3 square roots of 3. Again, you always want to simplify if you can. On example 5, you could start off by multiplying by the square root of 24 in both the numerator and the denominator. But I can see that I can simplify the square root of 24 first. 7 was a prime number and 3 was a prime number, so I knew I could not simplify these ones to start. But I can simplify the square root of 24. So let's start off by doing that. The smallest prime number that goes into 24 is 2. It goes in 12 times. The smallest prime number that goes into 12 is 2. It goes in 6 times. 2 goes into 6 3 times, and 3 goes into itself once. I have a pair of 2's that can leave my square root symbol. And then the 3 and the 2 are staying home. 3 times 2 is 6. So now that this is simplified, I can go ahead and say, all right, I want to rationalize my denominator. So I got to get rid of the square root of 6. So I can multiply both the numerator and the denominator by the square root of 6. By simplifying this first, it's going to make our lives a little bit easier. If you go ahead and just start multiplying by the square root of 24, you'll have to simplify again. So that's why I like to do it here, because it will make one less step for me at the end. So if I go ahead and multiply, I'll have the square root of 30 divided by 2 times the square root of 6 times 6 is 36. Let's see if we can simplify this at all. The square root of 30. If we try to simplify that, you will see that we do not have any pairs. We don't have any terms that can leave the square root symbol. So the square root of 30 is going to stay that way. What's the square root of 36? 6. So right now I have the square root of 30 divided by 12. I cannot simplify this any further. This is my answer. On example 6, let me try and simplify the square root of 12 to start. So 2 goes into 12 6 times, 2 goes into 6 3 times, and 3 goes into itself once. So I have a pair of 2's that can leave the square root symbol. And then 3 is staying inside the square root symbol. I want to rationalize this denominator, so I need to multiply by the square root of 3 in both my numerator and my denominator. In my numerator, I have to be careful. My numerator has 2 terms, so I need to be sure to put parentheses around that. That way I remember to use my distributive property. So 7 times the square, or 7 square roots of 3 times the square root of 3 will be 7 square roots of 9. Minus 5 times the square root of 3 is 5 square roots of 3. Divided by 2, and then the square root of 3 times the square root of 3 is the square root of 9. So let's try to simplify this. I'll have 7 times, what is the square root of 9? 3 minus 5 square roots of 3 over 2, and then you just told me the square root of 9 was 3. 7 times 3 is 21, and 2 times 3 is 6. This is my answer. Moving on to conjugates. The expression a plus the square root of b times a minus the square root of b are conjugates. When a and b are integers, the product a plus the square root of b times a minus the square root of b eliminates any radicals. Try these conjugates. So on example 7, we have 4 plus the square root of 7 times 4 minus the square root of 7. When you have 2 terms being multiplied by 2 terms, this is when we have been using the area model. 4 times 4 is 16. 4 times the negative square root of 7 is negative 4 square roots of 7. The square root of 7 times 4 is 4 times the square root of 7. And then positive square root of 7 times negative square root of 7 is negative square root of 49. So I have 16. What's 4 square roots of 7 minus 4 square roots of 7? 0. These cancel. Minus, what's the square root of 49? 7. Well, these are like terms. What's 16 minus 7? 9. This is our answer. Go ahead and pause the video and try number 8. So on number 8, I'm going to have the square root of 3 minus 4 times the square root of 3 plus 4. So I'm going to have the square root of 9, 4 square roots of 3, negative 4 square roots of 3, and negative 16. What is the square root of 9? 3. What's 4 square roots of 3 minus 4 square roots of 3? 0. These cancel. Here I forgot my square root symbol. What's the square root of 16? 4. Are 3 and negative 4 like terms? Yeah. What's 3 minus 4? Negative 1. This is my answer. On the next one, I'm going to do the same process. So I'm going to have 5 plus the square root of 5, and then 5 minus the square root of 5. So I'm going to have 25 minus 5 square roots of 5, 5 square roots of 5, and the square root of 5 times a negative square root of 5 is a negative square root of 25. So I'm going to have 25. What is the 5 square roots of 5 minus 5 square roots of 5? 0. Minus, what's the square root of 25? 5. What's 25 minus 5? 20. So notice how in all 3 of these problems, we didn't have any radicals in our answer. On this next one, it says, what is the conjugate of 2 plus the square root of 3? Well, the conjugate would be 2 minus the square root of 3. Remember, notice the only difference between these two is one has a plus and one has a minus here. We can use conjugates to remove radicals from denominators when the denominator is an expression such as 2 plus the square root of 3. Well, when we have two terms like this, we can use a conjugate to multiply both the numerator and the denominator. You just told me that the conjugate of 2 plus the square root of 3 was 2 minus the square root of 3. Because we're multiplying by two terms, we have to be very careful and make sure that we use parentheses. So in my numerator, 3 times 2 is 6, and 3 times the negative square root of 3 is negative 3 square roots of 3. In my denominator, we're going to be multiplying just like how we did with these ones up here. If it helps you, go ahead and write out the box. When I do that, I'm going to get 4, negative 2 square roots of 3, positive 2 square roots of 3. Those are going to cancel. And then I'm going to get negative the square root of 9. What's the square root of 9? 3. If you're confused on how I got this, all I did was this work up here. If it helps you, write that work out. So I have 6 minus 3 square roots of 3 divided by 1, because 4 minus 3 is 1. So I'm going to have 6 minus 3 square roots of 3 as my answer. Let's try that again with example 11. Here I have 3 divided by 4 plus the square root of 2. What is the conjugate here? Our conjugate will be 4 minus the square root of 2. And that's what I'm going to be multiplying by. So 3 times 4 is 12. And 3 times negative square root of 2 is negative 3 square roots of 2. To multiply these conjugates, you're going to do exactly what we did in these three problems. If it helps you, draw out your box to do that. So I'm going to have 4 plus the square root of 2 and 4 minus the square root of 2. 4 times 4 is 16. Here I'll get negative 4 square root of 2. Here I'll get positive 4 square roots of 2. And here I'll get negative square root of 4. So in my denominator, because that's what I'm doing right now, is I'm multiplying this part right here. So that's where we're existing. I have 16. What's 4 square roots of 2 minus 4 square roots of 2? 0. Those eliminate. Minus, what's the square root of 4? 2. So right now I have 12 minus 3 square roots of 2 divided by 16 minus 2 is 14. This is my answer. Let's go ahead and try example 11. On example 11, we have 1 divided by the square root of 3 minus 2. What is the conjugate? The conjugate would be the square root of 3 plus 2. So in my numerator, 1 times the square root of 3 is the square root of 3, and 1 times 2 is 2. In my denominator, when I go to multiply these, if it helps you, go ahead and draw out your area model. Square root of 3 minus 2, square root of 3 plus 2. The square root of 3 times the square root of 3 is the square root of 9. Here I'm going to get 2 square roots of 3, negative 2 square roots of 3, and negative 4. What's the square root of 9? 3. 2 square roots of 3 minus 2 square roots of 3 is 0. These cancel. And then I have my minus 4. So I have square root of 3 plus 2 divided by negative 1. Well, that's just going to be the negative square root of 3 minus 2. This is my answer. Go ahead and try example 12. If you're getting stuck on your conjugate, notice the only thing we ever changed was the middle sign. Our conjugate here would be negative 3 minus 2 square roots of 3. So again, with your conjugate, you're only changing the middle sign. The first sign doesn't matter. It's just the middle sign that changes. So when you go to use a distributive property, 2 times negative 3 is negative 6. 2 times negative 2 square roots of 3 is going to be negative 4 square roots of 3. And then in my denominator, I'm multiplying these conjugates together, so I am going to use the area model. So I'm going to have negative 3 plus 2 square roots of 3 and negative 3 minus 2 square roots of 3. Negative 3 times negative 3 is positive 9. Here I'm going to get positive 6 square roots of 3, negative 6 square roots of 3, and negative 4 square roots of 9. So again, we're working in our denominator. Right now I have 9. 6 square roots of 3 minus 6 square roots of 3 is 0. These eliminate. And then here I'm going to have negative 4 times, what's the square root of 9? 3. It's negative 4 times 3. Negative 12. So I have negative 6 minus 4 square roots of 3. And then in my denominator, what's 9 minus 12? This is technically your answer. Something that I notice is that every single thing is negative. So if I reduce, by negative 1, I'll have 6 plus 4 square roots of 3 over 3. If this was a test or a quiz and you left your answer like this, 9 times out of 10 I would take that. Because technically speaking, the only way to reduce here is negative 1. But just be careful and mindful of that.